Okay, I think we can start now. Do any of you have anything to ask? Before we start? Okay, so a couple of corrections to the last session discussion. This is what I was getting confused while explaining, and indeed this is not 0. Okay, in fact this is not 0. In fact the combination that becomes 0 is as follows: UR dagger P VS minus P. Okay, so these are all vectors, because remember in this solution P0 is always fixed. P0 is fixed to be square root of P square plus M square. Okay, because each of the components of Dirac-Spinner satisfies Klein-Gordon equation, and this is what you get, the dispersion relation for a Klein-Gordon field as well. So these are nothing but vectors you can think of, because P0 is nothing but related to this P vector. So if you take this particular combination UR dagger P VS minus P, then that becomes 0, but this combination is not necessarily 0. Okay. Are there any questions on this? Should I explain it again, or you remember what we discussed? Because these things will be useful today when we quantize the Dirac field and find out the Hamiltonian, corresponding Hamiltonian. Okay, you don't want me to repeat them, right? Am I audible?
Yes, no. Can you please have a glance at the glance?
Which part?
Just the last one.
So let us just look at this, the solutions. I mean, not the solutions the way we derived last time, but the normalization conditions and so on, which will be useful for the derivation of the Hamiltonian. So I'll repeat a bit maybe. Okay, another thing that I wanted to say before we start. Okay, I will say as we proceed. So, okay. So you wanted me to explain the last part, meaning before the quantization, right, Dhanush? Because at the very end we...
That wild spinner.
Wild spinners. Wild spinners? Not the solution, Dirac equation.
No.
Sorry, you want me to discuss the wild spinner?
No, not discuss. I just want you to have a quick glance, because that's what we are going to discuss right now, right? There is continuous.
Fine. Yeah, I understand. Okay. Okay, so just recap. So we have obtained the solution to Dirac equation, positive frequency solution, and which we wrote as u of p exponential minus I p dot x, and the negative frequency solution which was psi of x equal to v of p exponential I p dot x. For both these p0 is positive square root of p square plus m square, which is greater than 0. And then we substituted this in the Dirac equation. We first looked at the solution when the particle is massless, for a massless particle, and then we performed a boost to have arbitrary momentum in the z direction, and then we obtained the general solution. So the general solution was as follows: u of p was equal to square root of p dot sigma xi square root of p dot sigma bar xi. Now since in our chiral basis the generators lambda half turned out to be block diagonal 2 by 2 and then 2 by 2, so we said that the Dirac spinner can also have that 2 by 2 structure. So here indeed we have that, and so this is like a spinner that you usually are familiar with in quantum mechanics. So it's a 2 component spinner. So any 2 component spinner can be expanded as a linear combination of the basis 1 0 and 0 1. So any 2 component spinner you can expand as a linear combination of these 2 basis vectors, and we choose these basis vectors in such a way that xi dagger xi turns out to be 1. So that means xi 1 is equal to 1 0 and xi 2 is 0 1, so that this normalization property holds. Then the negative solution, negative frequency solution spinners are as follows: this is equal to square root of p dot sigma eta minus square root of p dot sigma bar eta. Again eta dagger, eta equal to 1. So that means the 2 possible choices are nothing but as that of xi, which is 1 0 and 0 1. So yeah, last time at the beginning I said that I will explain another way of getting this solution, which I forgot to do after I did that one particular way. So maybe I can, this is the right time to say that. So this is easier, but you need a guesswork to get this form. So let me start. Let me derive that. So start with that Dirac equation. I mean the positive solution to the Dirac equation. So psi of x equal to, let me not write it again, it's in the same page. This so if I substitute that here, I get p mu gamma mu p mu minus m u of p equal to 0. Okay, what is p? So p contravariant vector is p0 comma p vector, and gamma mu is this matrix 0 sigma mu sigma bar mu 0. Okay, and remember sigma mu is one identity and 3 Pauli matrices. Sigma bar mu is identity minus of sigma. Okay, so what happens to this quantity here? It becomes, in the matrix notation, it will become minus m multiplied by a 2 by 2 identity, sigma dotted with p, no sorry, not vector, it's 4 vector. So sigma mu p mu then sigma bar mu p mu minus m times u of p, so which we write it as ua ub. Since everything we are writing in 2 by 2 matrices, so the Dirac spinner, which is a 4 component spinner, we can break it up into two component spinners, ua and ub. Now, so what do we get from this equation? We get minus m ua plus sigma dot p. When we are not putting a vector and writing a dot in between, it means we are taking 4 vector dot product only. ub is equal to 0, and the second equation is sigma bar dot p ua minus m ub equal to 0. So now, so take ua to be square root of p dot sigma times some spinner, call it some spinner, let me call it gamma, no, that's bad notation, because gamma we are using for the matrices, so alpha maybe, so alpha, okay. So if we take this, so this is an ansatz that we are making. If we substitute u of a here in this second equation, so we have obtained these two equations from the Dirac equation, starting with the positive frequency solution. Now we are taking this ansatz for u of a. So what will be u of b from second equation? Take p dot sigma, not square root. So we will get sigma bar dot p, then sigma dot p alpha minus m ub is equal to 0. So for an arbitrary spinner, alpha, and we have derived last time that this is nothing but m square, so m square alpha minus m u of b equal to 0, so we get ub is equal to m times alpha. So what do we have for the spinner? That becomes p dot sigma, that's ua alpha times m alpha. To make this more symmetric, choose this alpha to be alpha is equal to square root of p dot sigma bar divided by m times some spinner xi. So therefore u of p will become p dot sigma square root of p dot sigma bar divided by m xi So we get square root of p dot sigma, and then within square root we have p dot sigma times p dot sigma bar, which is nothing but square root m square. That m square will get cancelled out with this m. So you get square root p dot sigma xi square root p dot sigma bar xi. But this method is easy to do, but the earlier one that we did, it was very rigorous. But here we are making ansatz and we want this kind of a form, and that's why we're choosing this alpha to be this and so on. But yeah, this is another way of obtaining the general solution. Okay. And let me pause and ask if there are any questions. Okay. If not, so we were summarizing. So this is another way of obtaining the general solution to Dirac equation. Just let me write that down. Now let us elaborate the normalization conditions of these spinors. So US dagger P UR P, this we saw last time, that this is I think twice EP times delta RS. So this would be xi r dagger square root of P dot sigma square root of P dot sigma bar times square root P dot sigma okay. So therefore this is equal to P dot sigma plus P dot sigma bar P dot sigma was equal to E minus P3 minus of P1 minus IP2 minus of P1 plus IP2 E plus P3. Okay, likewise P dot sigma bar E plus P3 P1 minus I P2 P1 plus I P2 and then E minus P3. So if we add these two, off diagonal elements are getting cancelled out, and in the diagonal we are left with twice E subscript P. So it's subscript P is to make sure that this E is nothing but square root of P square plus M square, which is P0. So we get 2 EP delta RS. Okay, and we said that this is not Lorentz invariant because we have this 2 EP here, this particular normalization, but this is useful for a massless particle because the other normalization, which is actually manifestly Lorentz invariant, turns out to be explicitly proportional to m, mass of the particle. So that normalization is not useful for a massless particle, and we have to use this other normalization. So U bar U, if we evaluate, U bar is U dagger gamma 0. This is U. What is U dagger gamma 0? Xi r dagger square root P dot sigma square root P dot sigma bar. Gamma 0 is 0, 2 by 2 identity, 2 by 2 identity 0. So it becomes, first element is xi r dagger square root P dot sigma bar, and the second element is xi r dagger square root P dot sigma. Okay, so therefore that normalization U bar U turns out to be square root P dot sigma bar sigma. US is square root P dot sigma okay. So we get P dot sigma bar square root plus the same thing, so twice square root P dot sigma times P dot sigma bar, and this is what, nothing but twice m, right? So this is twice m delta Rs. So you can see for massless particle this is identically 0. So these normalize, so okay. Okay, so this is these are the normalization conditions for the positive energy solution. Now similarly you can show that, so for the negative energy solution, the spinner was square root p dot sigma eta s minus square root p dot sigma bar eta s. So now V dagger V, put R here, is equal to eta dagger minus okay, sorry, so p dot sigma minus p dot sigma bar so this is again the same condition we get. As that of the positive solution. But if you do the other normalization, now what is V bar? This is eta r dagger square root p dot sigma minus eta r dagger square root p dot sigma bar multiplied by gamma 0 matrix times the solution now with parameter s. So this will become minus eta r dagger when you multiply by gamma 0 matrix. This will become minus eta r dagger plus eta r dagger square root p dot sigma okay. So you get minus p dot sigma bar square root, so 2 times eta s, which is minus twice m eta r dagger eta s minus twice m delta rs. Okay. Unlike the positive frequency solution, this normalization condition is having a minus sign in front, just coming from this minus here of the negative frequency solution. Okay. Yeah. Sorry, what did you say?
Scroll up.
Is it okay?
Okay.
Now, two other combinations that turn out to be 0, which I was not very clear about in our last session. I just want to explain that. So first of all, this we just said at the very beginning. Where was it? This combination. So this combination is not 0, but what turns out to be 0 is this. So let me just explain why that is the case. So U R dagger. Okay, so far we have seen the inner product of the positive frequency solution with itself and the negative frequency solution with itself. Now we want to see what would be the inner product between a positive frequency solution and a negative frequency solution. So U R dagger P V S P. This doesn't turn out to be 0. Likewise, dagger P U S P doesn't turn out to be 0. But the combination that turns out to be 0 is as follows: P Vs minus P. So let's see what is it. So this is equal to xi r dagger square root P dot sigma. Dhanush, mute yourself. Xi r dagger square root P dot sigma bar. Then Vs minus P. So what would that mean? So VSP is equal to square root P dot sigma xi s square root P dot sigma bar xi s. So what is P dot sigma? It's or sigma dot P. So it's sigma mu P mu, which is sigma 0 P0 minus sigma I or sigma dot P minus sigma dot P, because P mu is covariant index here. And so what would be? So what are we doing here? We are replacing P by minus P. That means in this solution it will become minus P dot sigma. Now minus P dot sigma is what? So if I make P vector to minus P vector, it will as if become sigma bar dot P, because sigma bar dot P is, what is sigma bar? Sigma bar is, here I just wrote, I think. It's too up. So sigma bar was identity and minus sigma. So if we replace P by P vector by minus P vector, as if we are replacing sigma by sigma bar. So this is sigma 0 P0 plus sigma dot P. So what we can write it as square root P dot sigma bar, okay, eta S, and minus, there is a minus here, square root of P dot sigma eta S. Therefore this will become xi r dagger square root P dot sigma bar eta S minus the same thing, xi r dagger square root P dot sigma bar times P dot sigma. So that's why this combination is 0. Okay. Likewise, VR dagger P US minus P also turn out to be 0 for same reason. So now this adjoint spinner would become eta r dagger square root P dot sigma minus eta r dagger square root p dot sigma bar, and us will be square root p dot sigma bar. We are replacing py minus p, so the first 2 by 2 spinner is multiplied by square root p dot sigma bar, and the next one by square root p dot sigma. Okay, so therefore this becomes, the first term becomes identical to the second, p dot sigma bar minus square root p dot sigma bar p dot sigma. So this is 0. Okay, and this will actually be useful when we derive the Hamiltonian. This particular two combinations will appear in our Hamiltonian, and those we will put to 0 because of this reason that they actually vanish. Okay, so we have discussed all the normalization, inner products of different solutions. Okay, are there any questions? It's clear, right, everything? So we will proceed to the normalization. Quantization, sorry. So before that, I now want to explain that while spinner a bit more. So here last time we discussed this while equation and helicity and so on. Okay, so the second correction to the previous session that I was planning to discuss is as follows. This helicity operator, we said that it is not a Lorentz invariant concept because it involves the direction of momentum, and we know that if we perform a boost, we can go to a frame where the momentum operator that we have in the previous frame can have different direction in the other frame. So the helicity operator is not Lorentz invariant concept in general, but for a massless particle this is always Lorentz invariant, because for massless particle we do not have a frame of reference where we can go and make the direction of spin opposite to that of the opposite to what it was in the previous frame of reference.
Okay, just repeat once again.
I am saying that for massive particle you can always go to a frame of reference because that is not moving at the speed of light. So you can always boost and go to a frame of reference where you can reverse the direction of momentum. But for a massless particle which is actually moving at the speed of light, you cannot boost and go to a different frame of reference which is moving faster than the speed of light. So you cannot, so for a massless particle, helicity operator is always a Lorentz invariant concept. So that's why massless particles, if you see, are sometimes characterized by the helicity. So helicity is a very important concept, but it's Lorentz invariant only for massless particles, and you can characterize any massless particle by its helicity because it will not change no matter which frame of reference you are in. So when I was explaining this helicity operator, and then we said that U1 is an eigenvector of helicity operator with eigenvalue plus f. Well, it's mathematically happening, but this is not very good way to say it, because here the particle is actually massive. So its mass, it's E equal to square root of P3 square plus M square. Here, for these solutions that we have written down, U1P and U2P. But since helicity is not Lorentz invariant for a massive particle, what we should instead write is first take the massless limit of these solutions and then see what is the helicity, what is the eigenvalue corresponding to the helicity operator. So by that I mean for a massless particle, so let me just write these things down here. Maybe I will add a page and I will replace this file on the drive folder. Add a page after current input. Is not Lorentz invariant, not a Lorentz invariant quantity for massive particles, but for massless particles helicity is always Lorentz invariant. Is a Lorentz invariant. So in the massless limit, u1 of p, which was equal to square root of e minus p3, square root of e minus p3 1 0, square root of e plus p3 1 0, as m tends to 0, what will it become? E3 will become equal to p3. So we get 0 0 square root twice e 1 0. Okay. So now, since helicity is Lorentz invariant for this kind of a state, it's for this kind of a particle which is massless, we can say that this is always an eigenstate of the helicity operator with eigenvalue plus half. So helicity operator acting on, so this is u1.
How it become like this after m tends to 0?
Yeah, because E is square root of p square plus m square. Now we have boosted the rest frame solution to a frame of reference where we have momentum only along the third direction. That's why only p3 was non-zero. p3 is non-zero. So it will become p3 square plus m square. Now in the massless limit, E equal to p3. Okay. So once E equal to p3, this is square root 2e and this is 0. So you get this solution. So here this p is nothing but u1 of E. So when m equal to 0. So therefore this u1 E is an eigenstate of the helicity operator with eigenvalue plus half. And this is always the case. And remember, what was the helicity operator? Helicity operator is projection of the spin along the direction of the momentum. Okay, and spin for us, the wild basis that we have chosen for the Dirac matrices, it was Sij was equal to half epsilon ijk sigma k 0 0 sigma k, or we can write it as, so S vector will be just half sigma vector 0 0 sigma vector. So So when the particle is moving along the z direction, so it's p3 dotted with s, p3 unit vector dotted with s, that becomes half sigma 3 0 0 sigma 3. Okay, so this is nothing but half of the helicity operator is half of 1 minus 1 1 minus 1. Okay, and likewise u2 of p was it was 0 square root p e plus p3 0 square root e minus p3. So it was square root of e plus p3 0 1 square root of e minus p3 0 1. Okay, this in the massless limit will become square root twice e 0 1 0 0. Okay, so now this helicity operator, if you act on this, so call it u2e, because p3 is now just e for massless particle. So h acting on u2 will be minus half, because you can see there is minus 1 here, the 2 element of the helicity operator, minus half. So therefore u2 is an eigenstate of with eigenvalue minus half. Okay, so what I will do is remove this particular page and put it in the next one. Bear with me. Okay, good. Now let us also talk about that chirality operator a bit before we do the quantization. Yeah, so chirality we want to talk about. So the basis that we have chosen was Weil basis, which is also called chiral basis. Okay, and we have seen that in this basis our rotation matrix lambda half for rotation, that became exponential of minus I theta dot sigma over 2 0 0 exponential minus I theta dot sigma by 2. Okay, where theta are the 3 rotation parameters, meaning omega 1 2 is equal to theta 3, omega 2 3 is theta 1, omega 3 1 is theta 2. Okay, so if you use that use these things in the generator, use these things in that expression lambda half. So lambda half, what was lambda half? It was exponential of minus I over 2 omega mu nu s mu nu. We are talking about only the rotations. So the relevant parameters are omega 1 2, omega 2 3 and omega 3 1, which we are taking to be theta 1, theta 2 and theta 3. That is what we are writing here. And you already know what is Sij. I was just telling few minutes back. It's epsilon ijk sigma k 0 0 sigma k. So what is S12? S12 is half sigma 3 0 0 sigma 3 and so on. So this gets multiplied by theta 3 and so on. S23 will be multiplied by theta 1, and that's why you get this dot product here. Okay, good. And here there is this summation over mu and nu, which to take care of the fact that omega 1 2 S12 is same as omega 21 S21, we have divided by this 2 factor here, and this 2 that is appearing here, that is coming from this generator. Okay, so this is what the rotation matrix look like in the while basis. So you remember, right, where this while basis was useful? It was useful to obtain this particular form of Sij. So what was S mu nu? S mu nu was I over 4 gamma mu gamma nu. These are the generators according to which a spinor transforms, not a vector. A 4 component spinor transforms under the transformation of these type of generators. So just to recap, so a spinor psi alpha, which is a 4 component spinor, it's lambda half alpha beta psi beta. Okay, so and these are the corresponding generators for this particular transformation under Lorentz transformation. Okay, so having said all of this, now let's write what was the boost matrix. Lambda half corresponding to boost, it was exponential of was it minus or plus? Minus so S0I was I over 2 minus sigma I 0 sigma I. So just like Sij is that quantity, we also derived S0I, that turns out to be I over 2 minus sigma I 0 0 sigma I. Okay, so if we now substitute this in this expression, so let me see. So there is I here, so I square will become minus 1, it will become plus. Okay, so that means the first quantity will be plus no, so I here and then this I will make it I square, so that is this will become plus, but here I have a minus. Okay, so this is equal to, call the parameter to be beta. Okay, don't confuse between this notation alpha and this beta. This is okay, let me use something else, maybe phi minus phi dotted with sigma divided by 2 0 0, and this element will become exponential of plus phi dotted with sigma divided by 2. Okay, so now the point is that this particular while basis helped us to get the Lorentz transformation matrices under which a spinor transforms as diagonal, like 2 by 2 block diagonal. Both are 2 by 2 block diagonal. So that's why we wrote down the chiral. Sorry, yeah, go on.
Yeah, I have a simple doubt. Can I ask it right now?
Sorry?
So this beta, I have a doubt. Can I ask it now?
Yeah.
So the beta in the boot that correspond to V by C, right? Ratio of V to C.
Say that again.
The beta or phi that you are just putting in the exponential term, that's nothing but V divided by C, right?
No, this is the parameter. No, it has nothing to do with that beta. No. And I haven't put beta here. Why do you see beta?
No, but you just replace beta by phi because we don't want to use the same thing again.
Yeah. Okay. No. This is just the parameter. This is the amount by which you are, like this theta here denotes the amount by which you are performing the rotation.
Okay.
So in that sense, this beta should have, or phi should have interpretation of the amount by which we are performing the boost. So
yeah, then it will be that beta only, right? Beta by C, right?
Yeah, you are correct. Yeah, it's better we put beta here, and that vector notation shows the velocity, direction of the velocity.
So the exponential term above that, everything is the dimensionless quantity, right?
Because it's the velocity, you are asking whether it's. Yes.
I'm just talking about both the terms, the theta dot sigma and beta dot sigma. Both things are dimensionless quantity, right?
Both are dimensionless
quantity. Am I right?
Yeah, inside the exponential, it has to be dimensionless. So yeah, it's V by C, it's dimensionless. Yeah.
Okay, that's what I just want to clarify.
Yeah, good question. Yeah, it's better that we keep beta, and maybe we can use some other notations here. A, B, B. Okay. Yeah, so this particular form of the transformation matrices helped us to get the Weil spinors, right? So we wrote a Dirac spinor psi as psi L and psi R, and we saw that they satisfy Weil equation for a massless particle. So should I repeat that? So it was I gamma mu del mu minus m acting on psi equal to 0. So that would give you minus m I sigma mu del mu I sigma bar mu del mu minus m acting on psi L psi R equal to 0. So there is one subtlety that I want to point out here, that's why I am telling this again. This acting on equal to 0, that is one equation, and the other equation is I sigma bar mu del mu psi L minus m psi R equal to 0. So you can see if the particle is massive, you need both these psi L and psi R, both these two component spinors. But for a massless particle, you get two decoupled equations for psi L and psi R. And these two are the while equations. And psi L and psi R are called while spinors. Two component while spinors. And you also know how they transform under the Lorentz transformation. So because we had this particular form of the transformation matrices, we immediately know how they transform under the Lorentz transformation. So they transform as, the infinitesimal transformation would be so psi L would transform under this, and this for rotation and this for boost. So we can write it as 1 minus I theta dot sigma over 2 minus beta dot or we can write it as this way. So under rotation, psi L and psi R both transform in the same way, that is they transform as exponential of minus I theta dot sigma divided by 2 psi L. Psi R also transform in the same way, exponential minus I theta dot sigma over 2 psi R. And under boost, psi L transform as exponential minus beta dot sigma divided by 2 psi L, and psi R transforms in the opposite way. So we know the transformation properties of these while spinors because we have chosen that while basis in which the generators are block diagonal. The transformation matrices are block diagonal. But now suppose we want to define these chiral spinors for any general choice of the basis. Choice of the basis of the matrices which satisfy that Clifford algebra. Okay. How do we do that in a Lorentz invariant way? So that's the question that we want to ask. And the answer is as follows. We have to define a fifth gamma matrix. So let me just write down what we are asking. So for an arbitrary choice of basis for the gamma matrices, can we get this chiral spinors in a Lorentz invariant way? So the answer is yes, of course. And for that, let's introduce this gamma 5 matrix, which is I times gamma 0, gamma 1, gamma 2, gamma 3, which satisfy this properties that gamma 5 square is identity and gamma 5 anti-commutes with all the gamma mu matrices, and gamma 5 dagger is gamma 5. Okay, so this suggests that, this immediately tells that S mu nu, the generators of Lorentz transformation for the spinner, commutes with gamma 5. Is this clear to you, or should I explain it? Like, you know how S mu nu is defined. If gamma 5 anti-commutes, you can also check that gamma 5 anti-commutes with all the gamma mu matrices from this expression of gamma 5. I won't be deriving it because I will not have time to do the quantization. So you can check this by yourself. It's easy to check. Just verify it. So this shows that, what does it show? It shows that gamma 5 actually commutes with that lambda half matrix. So gamma 5 transforms as a scalar under Lorentz transformation. So we can use this gamma 5 to define two projectors P plus minus, which is 1 plus minus gamma 5 divided by 2, acting on, this is the projector. Why do we call it projector? Projector has these properties that P plus square should be equal to P plus, likewise P minus square should be equal to P minus, and that is indeed the case, because if you multiply 1 plus gamma 5 divided by 2, if you square it, we will get 1 plus 2 gamma 5 plus gamma 5 square. What we said, gamma 5 square is identity, 1 divided by 2. Okay, remember that all these gamma 5, this gamma 5 is actually a 4 by 4 matrix, because you know the gamma matrices are all 4 by 4 matrices. So when we are writing 1 plus gamma 5, here this 1 means a 4 by 4 matrix. So keep this in mind. So this is 1 plus gamma 5 over 2, which is P plus. Likewise P minus square will be P minus, and P plus P minus is 0. These things you can check. Now this projector P plus, when acts on a Dirac spinner, it gives psi plus minus. So, and this psi plus minus are actually eigenstates of gamma 5 operator with eigenvalue plus and minus. So let me illustrate this with the basis that we have chosen, and then we can come back to this general statement. So for the while basis, gamma 5, you can check that this is minus 1, 0, 0, 1. So you know all the gamma matrices. You can just substitute those here and check that gamma 5 turns out to be minus 2 by 2 identity, 0, 0, 2 by 2 identity. Okay. So what will be then P plus? P plus acting on psi will be equal to, what is P plus? P plus is 1 plus gamma 5 over 2, right? So that is 0, 0, 0, 1 acting on psi, psi L, psi R. Okay, so we get 0, psi r. Let's call it psi plus. Okay. So you can see that with our choice of while basis, P plus actually projects the spinner psi r, and gamma 5 acting on psi plus will be equal to gamma 5 plus gamma 5 times 1 plus gamma 5 psi plus, which is equal to plus 1 times psi plus. Sorry, I think this is becoming very abstract, but just ask me questions, then it will be probably clear to you what I am trying to say. So psi plus is an eigenstate of gamma 5. Gamma 5 is also called the chirality operator. Eigenstate of gamma 5 with eigenvalue plus 1. Likewise, gamma 5, okay, likewise P minus acting on psi will be identity 0, 0, 0 side psi L and psi R. So this will become, this is psi minus, eigenvalue plus 1, and this is called right-handed spinner. Okay, so P minus acting on psi is projecting out psi L, which we are calling psi minus. Psi minus is a 4/1 spinner. Psi L is a 2/1 or a 2 component while spinner. Okay, and this psi minus is what we call the left-handed spinner, because gamma 5 when acts on psi minus, it gives eigenvalue minus 1. Okay, so this you can see, because gamma 5 acting on psi minus is P minus acting on psi, which is 1 0 0, sorry, 1 minus gamma 5 over 2 psi L. So this will be gamma 5 minus gamma 5 square by 2 psi L, sorry, not psi L, yeah, psi. One minus gamma 5 minus 1 over 2 psi, which is minus 1 times psi minus. So psi minus is an eigenstate gamma 5 with eigenvalue minus 1, and this is called left-handed spinner. Okay, let me pause and ask if there are any questions. So this is all I wanted to talk about this chirality operator. and the left-handed and right-handed spinner in general. Okay, so this is what we obtain for our choice of basis. So gamma 5 turns out to be -1001 for the choice of basis we have chosen, and in principle for an arbitrary choice of the basis, this is how the left-handed and right-handed spinners are defined in terms of the chirality operator gamma 5. So this is 1 plus minus gamma 5 by 2 acting on psi. Okay, and psi plus will be the right-handed spinner, psi minus will be the left-handed spinner. And the choice of basis that we have made, P plus projects onto psi r, which is the 2-component wide spinner, and P minus projects onto psi L, which is again the 2-component wide spinner, which satisfies the Weil equation in massless limit. Are there any questions? Okay. So let me go back to the quantization. I don't know how much I could explain this chirality part, but let me know if you have any questions later on. So I asked you to show this particular anti-commutation relation, starting with this, assuming that creation annihilation operators satisfy this relation, and this is how we expand the spinner in terms of the positive frequency solution and negative frequency solution. Has any of you tried this? So let's start the quantization. So since we are dealing with fermions, which has to satisfy Fermi-Dirac statistics, the spinners must satisfy anti-commutation relation, unlike the commutation relation of the Klein-Gordon field. So our first step is to promote the field, Dirac field, or the Dirac spinner, to an operator and write this canonical commutation relation, that psi x psi dagger y is equal to delta 3 x minus y psi x psi y psi dagger x psi dagger y, these are all 0. Okay, and we expand the spinner as a linear combination of the positive frequency solutions and the negative frequency, just the way we did for Dirac, just the way we did for Klein-Gordon field as well. So now we also have to incorporate the spinners, not just the creation and annihilation operator. So AP summation over S, okay, U exponential of pi p dot x plus times b exponential minus I p dot x. Okay, what is psi dagger? Summation over s.
This one?
Yeah.
Oh, okay. Okay.
d3p over 2 pi cube. So this I wanted to say. Here I think I wrote the other way around. It should be plus and it should be minus. So that when we write down the corresponding Heisenberg picture operators, we get the correct sign. We get exponential minus I p dot x for the positive frequency solution and exponential minus I p dot x for the negative one. So this is plus and this is minus. So this is dagger exponential I p dot x plus exponential minus I p dot x. Okay. So yeah, and the claim is that for this anti-commutator to be true, to be satisfied, the anti-commutation relation that these creation annihilation operators has to satisfy is as follows. It's AP is this is equal to 2 pi cube delta RS P minus Q. Likewise, two pi cube and all other anti-commutators vanish, meaning anti-commutation between A and B vanish, A dagger, B dagger vanish, A dagger, B vanish, and so on. Okay. So we want to check this statement. So we will start with this psi and psi dagger expressions. Use this property and try to get this. Okay, that is what we want to do first. So let's proceed. So psi x, psi dagger y. This anti-commutator we want to find out. So this is equal to summation over R is integration d3p d3q 2 pi to the 6 twice square root EP PQ. Okay. Then anti-commutation between psi and psi dagger. So psi we write as APR. So let me just copy that from here. So yeah, so this is psi comma psi dagger. Okay, we are using R index for here. R superscript. So, and for psi dagger, let me copy this. Okay. Okay, so we are performing this anti-commutation. Okay, now we have to keep in mind that this is in variable q and y. So p dagger q dot y okay. So what will it be? It immediately boils down to just two terms, because as we said, this anti-commutation with this will survive and this with that will survive. So we get two terms. So let's write that d3p d3q over 2 pi to the 6 2 square root of ep eq, anti-commutation between ARP AS dagger Q UR US dagger Q. Okay. Exponential. What do we have? I p dot x minus q dot y, okay, plus p q vr vs dagger exponential of minus I p dot x plus q dot y. Okay. Now let's use the anti-commutators here and here. So it will give 2 pi q delta rs times delta 3 p minus q. So let's summation over rs. I will keep delta rs outside. Delta 2 pi q will cancel out 1 2 pi q here. So d3p d3q 2 pi q 2 square root of ep eq. We have delta 3 p minus q urp us dagger q exponential I p dot x minus q dot y plus another delta 3 will come for that term. So I'll take delta 3 common, vrp q exponential minus I p dot x plus q dot y. Sorry, I think I made a mistake here. So when I am writing this particular commutator, this is getting multiplied by this. So if I take minus outside, this will be minus, right? So this multiplying this gives that. This will be so this will be minus here. Everything else is fine. So this is minus. Okay, So let's now take the summation over R. So that will give us summation over S, and also integrate over Q. So we are left with 2EP US dagger P exponential I P dot x minus y plus VS dagger P exponential minus I P dot x minus y. Clear? Now remember the completeness relations that we derived last time. I'll just state. Summation over S US P U bar S P was gamma dotted with P plus M, and VS P V bar S P was gamma dotted with P minus M. Okay, so you see we have U dagger and V dagger here. So what we can do is multiply by gamma 0 square here, because gamma 0 square is 1, so we can always do that. So we'll be left with 1 gamma 0, and another gamma 0 we can take with U dagger and V dagger to make it U bar and V bar. You get what I'm saying? So this is equal to summation over S integration d3p over 2 pi q 2EP. Okay, so summation over S we are taking inside to write this particular relation. So we get gamma dot P plus M times gamma 0. Let me know if this step is unclear. I P dot x minus y, okay, plus gamma dot P minus M times gamma 0 x minus y. Okay. Now so this we can expand. Gamma dot P we can write as gamma 0 P0 minus gamma dot P plus M gamma 0 P dot x minus y plus gamma 0 P0 minus gamma dot P minus M gamma 0 exponential minus I P dot x minus y. So in the last term we can replace P by minus P, because that's the integration variable. We can do that, and that will give us first term remains as it is. In the second term I am replacing P vector by minus P vector. So it will become, so this term gets cancelled with that, and these two also gets cancelled out, and we are left with, so gamma 0 square is identity, so two terms are now same, so 2 times P0, and P0 is nothing but E of P, E subscript P. So this gives d3p over 2 pi cube exponential I P dot x minus y, which is the delta function, 3-dimensional. Okay, so this is what we,
just a minute. If you change P to minus P, then the d3p is also changed, right?
Similarly the integration limit which which is from minus infinity to plus infinity, will become plus infinity to minus infinity, which if you change, then d3t will be plus.
Okay.
Okay, so everything is good. So now let's derive the Hamiltonian, and the propagator and all we can discuss next time, and then we can also start the interacting Lagrangian and so on. So what is the Hamiltonian corresponding to the Dirac Lagrangian? So Lagrangian is Lagrangian density gamma mu del mu minus m psi. If we write it explicitly, it becomes gamma 0 del 0 plus I gamma dot del minus m acting on psi. What is the conjugate momentum corresponding to psi? It's del L del psi dot, which is nothing but I psi bar gamma 0, which is same as I psi dagger. Okay, so the Hamiltonian density will be pi psi dot minus L, which is I psi dagger psi dot minus L. So this term is same as this first term there. So therefore the Hamiltonian density is minus I psi bar, the Hamiltonian density will be minus psi bar I gamma dot del minus m psi. Okay, or the Hamiltonian is d3x times the Hamiltonian density, which is d3x times, let's put the minus inside, gamma dot del minus m, that will become plus now psi. Okay, so this is what we want to evaluate. We have psi side and the expansion of psi we have written earlier, so that's what we are going to use. Okay, so first we evaluate this particular part and then we will multiply by psi bar. Okay, so let's do that. So minus I gamma I del I plus m acting on psi is equal to plus m acting on this, so summation over s. Okay, so this is equal to, so del I when act on this exponential I p dot x. Okay, now remember this is a spinner, 4 component spinner. This is also a 4 component spinner, and gamma matrices may not necessarily commute with these spinners. So what we should do is we can take this operator here, but we shouldn't take this operator to this side. So this is equal to
Read again.
I'm saying that these are matrices 4 by 4 gamma I, and this is a 4 by 1 spinner. Yeah, and so I'm saying that matrices may not necessarily commute, so we can take this differential operator at this position, but we shouldn't take it to the right of that spinner. Okay, so I'll write it, then it will be clear to you what I'm saying. So summation over S d3p over 2 pi q 1 over square root 2 ep asp. Now this is just exponential I p dot x. This we can keep here also. I mean, so this differential operator, when acts on this exponential, it will bring down I times p vector. So that will give gamma dot I square minus, so it will be plus gamma dot p plus m times exponential pi p dot x, okay, plus then here we will get minus gamma dot p plus m times v. Okay. Now remember the Dirac equations written in this spinner u and v, written in terms of spinners u and v. So I gamma mu del mu minus m acting on psi. If you write in terms of the positive spinner's solution, exponential of minus I p dot x. So that gives us gamma mu p mu minus m. So this is gamma 0 p0 minus gamma dot p minus m. So what do we get? Gamma dot p plus m acting on the Dirac spinner is gamma 0 p0 acting on the spinner. So we can use this over here to replace that by gamma 0 p0 u p. Okay. Likewise, for the negative frequency solution, we have, if we replace the negative frequency solution, which is v exponential I p dot x, so we get minus gamma mu p mu minus m. So that is minus gamma 0 p0 plus gamma dot p minus m. So from here we see that gamma dot p minus m acting on v is gamma 0 p0 times p, and this we can replace here. Okay. So therefore,
Can you scroll down that last?
Therefore, this is equal to let me copy this, then I'll scroll down. This is equal to summation over S T3P over 2 pi Q 1 over square root 2 EP this is gamma 0 p0 p dot x plus gamma 0 p0, sorry, is everything fine here? Yeah, I guess so. Gamma 0 p0 b is okay. So this is what we get now. This entire thing will be left multiplied by psi bar, okay, to get the Hamiltonian. So the Hamiltonian, what's the time? Okay, so let's left multiply by psi bar. So first of all, psi bar is psi dagger gamma 0, so it's psi dagger gamma 0, and you can see this expression, which is for this expression, we have gamma 0 here. So this gamma 0 when gets multiplied, that become 1. So we are left with d3x psi bar, psi dagger. Let me copy psi dagger also from above. So that's psi dagger. Yeah. Let's put R. Okay, and for this summation over s d3q, it will become 2 pi to the 6 square root of 2 times square root of ep eq times a is. Just let me know if you point out any mistake anywhere, because this is very lengthy. So P0 I'm taking outside. So P0, let's put it here. Okay. So U is P exponential I. Okay, sorry, we are using Q here. Exponential I q dot x plus q dot x. Okay, I hope everything is fine. Okay, so now we need to multiply. We get 4 terms. Summation over r is integration d3x d3p d3q over 2 pi to the 6 P0 divided by 2 square root. The last term is okay. So see, there is this P3x which when multiplied by this exponential, that will give us a delta function. So we get so integration over d3x will give delta, so these terms will be replaced by delta functions. So we have delta 3 p plus q, delta 3 p minus q, delta 3 p minus q, and delta 3 p plus q. Okay. Now let's integrate over q variable, so that would imply we have d3p over so we required one 2 pi cube also in order to replace this by delta function, so it becomes 2 pi cube here. Okay, because integration d3p over 2 pi cube times exponential of that function will give you delta 3 p plus q or whatever. So now taking the integration over q, so no matter whether q is minus p or plus p, this e of q will always give you e of p, because eq is square root of q vector squared. So whether it's minus or plus doesn't matter, it will become e subscript p. So that gets cancelled out with this p0 here, because ep is nothing but p0. So we have half times, so we are integrating over q. So for the first term, q will become minus p, br p, this is minus p, now you can see why those conditions we wrote down at the beginning, so those will be useful here. As you can see immediately that the first term is 0 because of this combination, plus A R dagger P, A S P, U R dagger P, P. Now you can also recognize this, and you now know what it is, plus B I think something is missing. Just a moment. Let me check. Oh, here I missed one thing, I think. So I square, just give me 1 minute. So this I square is minus, and then there was this minus. So minus, and then this became plus, and what, oh, see here we had minus of gamma dot p plus m. Okay, so minus of gamma dot p plus m will give a minus sign here. So the minus sign is actually very important, otherwise we were about to get a negative tower of energy. So let me incorporate that minus sign. I'm sorry about this. So this is minus here. Okay, so this term is minus. Then the last two terms will be minus. This is minus. Just let me see. Yes, this is minus, and this is also minus. Okay, so this is minus. BQ is dagger P. Okay, we are taking the integration over Q, so it will become P. Okay, minus AR dagger. Sorry, I think I'm overshooting. Just I'll take another couple of minutes. Is dagger UR dagger P. Okay, so here Q is minus P, so V is minus P. Okay, everything clear? So now you know that PR dagger P US minus P equal to 0, UR dagger P US P equal to 2 EP delta RS. BR dagger P BSP is similarly and times ps minus p, this is 0. So the first term and last term vanishes, and the remaining two terms give us Hamiltonian is equal to summation over rs integration d3p over 2 pi cube half of, so 0 plus, I'll not write 0, 2 ep delta rs ar dagger p asp. The next term is minus 2 ep delta rs bpr is dagger. Okay, so 2 gets cancelled out. We can take summation over r, so because of that delta function, 2 pi cube ep, taking outside we have minus but now we can use the anti-commutation relation to write that term as plus the another constant term which even if infinite constant, we don't care about it because we are only interested in the energy differences. So this is the Hamiltonian. Okay, so this is similar to what we have obtained for complex Klein-Gordon field, but now there is a summation over S which takes values 1 and 2. Okay, let's have more discussions on it in our next session, and I'll also describe the Feynman propagator for the Dirac field, and then we'll start next things, interaction. I find very difficulties in understanding symmetries in classical field theory, which in week 7 are you writing anything else? Do you have any specific question from week 7? Because I haven't seen those lectures, so I don't know what was taught there. So can somebody tell me, like, yeah, I understand, but what is being taught there? Is it Noether's theorem?
It's the basics. No, it's the basis of symmetries, not Noether's theorem. Noether's theorem comes under week 8. It's basics of some symmetries.
What kind of symmetries? Parity symmetry?
Exactly, parity, space-time, and then
Look,
I think he used between the global symmetry and local symmetry.
so exponential I alpha times phi is a global symmetry of the Klein-Gordon field. Yeah,
that's what it is.
Can you tell me, Rooney, if you have any specific questions, like where are you facing difficulties, like which portion you want me to explain? I didn't any of it. If you unmute yourself and then say, it will be better, because yeah. So maybe in the next class you try to write down your doubts, and then maybe you can share your screen and let me know where are you facing difficulties, and then I can explain to you those things. Is that okay? Okay, great. So let us stop here and meet next week. Okay, yeah, no problem. Let's meet next week, and let me know your questions. Specific questions you try to write down, where are you facing difficulties, and then I'll be able to take care of those. Okay.